This is worksheet 2 for chapter 6, differential equation practice. So these are very kind of unique type problems. So I wanted students to be able to be familiar with these types of trial and error, a little bit of it, trial and error take on these differential equations. So we have a function y equals e to the 3x minus 5x plus 7. It's a solution to which of the following differential equations? And we have a bunch of options, y double prime involving y prime. So I think the easiest way to kind of piece together this puzzle, let's go ahead and find y prime and y double prime. And I think from there we can kind of see how things fit together to allow for different variations of second derivative and derivative and terms that will total to be 0. Okay, so a little bit of trial and error. But first, let's gather information from first and second derivative. So just as a review here, to recall, the derivative for e to the u is e to the u times u prime. So e to the 3x is just e to the 3x times 3. Derivative that is. 5x becomes 5. 7 goes away. So here's my y prime equation. If I want to find my y double prime, which is something that I need. So the derivative for e to the u is e to the u times u prime. So I have e to the 3x times 3. 5 goes away to just 0. I can push those 3's together to make it y double prime is equal to 9e to the 3x. So how can I find a way to combine y prime and y double prime to allow for one of these answer choices to be true? So let's look at the first answer choice here. What if we do y double prime minus 3y prime minus 15 equals 0? Can we make the appropriate substitutions and see if this ends up being a true statement? So y double prime we found to be 9e to the 3x. Y prime we found to be 3e to the 3x minus 5. Okay, so again, this is a prime notation there. We get 3e to 3x minus 5, so we make that substitution there. Minus 15. Okay, so we're not doing anything derivative involved. We're just putting stuff in and see if this ends up being a true statement. So if I distribute the 3 through, I get minus 9e to 3x plus 15. 15's cancel out. The 9e to 3x cancels out. I'm left with this being a true statement. So option A is true. So I didn't have to go through and test the other ones. But if I tested one that was incorrect, then I should be able to tell, when I plug something in for y double prime and y prime, I'm not able to get that 0 to be true. I'm not able to get everything to cancel out. So none of these other ones will cancel out nicely. The only one that will allow for our substitution and following steps, all the terms canceling out, is option A. Answer choice A. All right, so we have a differential equation here. We're going to find the appropriate equation by appropriate solution by cross multiplying. So I'm going to rewrite that y secant squared x over as y secant squared over 1. Cross multiply here, I get 1 dy is equal to y secant squared x dx. Divide both sides by y. So I have 1 over y dy equals the integral of secant squared dx. Left side is just natural log. Right side, we have a rule for secant squared, which is tangent, plus c. So once we have our general equation, we want to eventually move our way to solving for y. So to do that, we're going to raise both sides, base e. That will allow for this to clean up nicely to be just absolute value of y is equal to e to the tan x plus c. We can split that up as e to the tan x times e to the c. And then e to the c is just a constant. Push that constant in front. We now have a cleaned up general equation. So now we have an ordered pair that we can use. Ordered pair is 0, 5. So 0 plugs in for x, 5 plugs in for y. Let's see where that takes us. Tangent of 0 is just 0. E to the 0 is 1. So c times 1 is just c. c equals 5. Once I have my c value, I'm going to update my general equation from general to specific. Replace the c with 5. All right, number 2, which of the following is the solution to the differential equation with the initial condition y of 0 equals negative natural log of 4. So again, I'm going to cross multiply here, rewrite that e to the y plus x as e to the y plus x over 1. Cross multiply, I get dy is equal to e to the y plus x dx. Now, we got to go a little further. This is still not ready for antiderivative. Notice that this y is not in the right location, but it's not easy to just bring that y over. So maybe I can clean this up a little bit more. I'm going to continue to expand this out. E to the y plus x, same thing as e to the y times e to the x. And now I can more easily move some things around, right? I can divide both sides by e to the y. Bring that e to the y up, and now we can get both, we can apply e to the u rule for both sides. Here I have e to negative y, so I need to force that to be our u value, which will produce a negative 1 derivative. E to the x is just e to the x. We don't have to go through u substitution there. So when I go through u substitution on the left side, that negative is going to carry over to my antiderivative. So I'm left with negative e to the u, which is negative e to the negative y. If I go back and replace the u with the original variable. And the right side is clean. It's just e to the x plus c. I'm going to go ahead and try to solve for y first. So I'm going to multiply everything through by negative 1. I want to bring that y down, so take the natural log of both sides. Bring that negative y down, natural log of e goes away. And now I have my general equation. I'm going to use my order pair to plug in and solve for c. So 0 plugs in for x. Negative natural log of 4 plugs in for y. So once I make that substitution, I'm going to try to solve for c. So I'm going to drop the two negatives. I'm also going to raise both sides, base e. When I raise both sides, base e, or once I get rid of the negatives and raise both sides, base e, I'm able to get it down to 4 is equal to negative 1 plus c. All right, get that negatives to go away. So 4 is equal to negative 1 plus c. Add 1 to both sides, we get c equals 5. So y is equal to negative natural log, negative e to the x plus 5. Number 3, a curve has slope 2x plus 3. This is a little confusing here. Slope 2x plus 3, that's not a constant slope, so we need to think of that as a derivative equation. So we're going to think of that as dy dx equals 2x plus 3. The wording is a little strange there. Which of the following is an equation for this curve that passes through the order pair 1, 2? So I'm going to get this to be separation of variables. I'm going to go through separation of variables. So dy dx equals 2x plus 3 over 1. Cross multiply, get 1 dy is equal to 2x plus 3 dx. Take the anti-differentiate both sides. 1 becomes y. Power rule on the right side. 2x becomes 2x squared over 2. 3 becomes 3x plus c shows up. Clean this up. We get the 2's to cancel out. Use the order pair to update our general equation to a specific equation. So let's plug 1 in for x, 2 in for y. 2 is equal to 4 plus c. c is equal to negative 2. I can update my c with negative 2. So there's my specific equation. Answer choice D. Number 4, for what value of k, if any, will k is equal to k sine of 5x plus 2 cosine 4x be a solution to the differential equation y double prime plus 16y equals negative 27 sine of 5x? So we know we have to, before we can do anything with this, we need to know what y double prime is. So let's work our way down to y double prime and we'll have a better idea maybe how things can fit together. So let's find y double prime. Remember, k is just a coefficient. It's just a number. So when we find the derivative, this feels like you may have to go through product rule, but there's no need for product rule. The k is just a coefficient. Treat that like a 2 or 3 or 5. So the derivative for k sine of 5x, it's really just sine of 5x we have to worry about. Sine of u becomes cosine of u times u prime with the k in front. Cosine of u becomes negative sine of u times u prime with the 2 in front. So if I clean this up, I get y prime is equal to 5k cosine 5x minus 8 sine of 4x. Okay, so we'll repeat the derivative process again to get from y prime to y double prime. Again, 5k is just a number that hangs out in front of my variable expression. Cosine of u becomes negative sine of u times u prime with the 5k hanging out in front. And then sine of u becomes cosine of u times u prime with a negative 8 hanging out in front. So this cleans up to be negative 25k sine 5x minus 32 cosine of 4x. So let's make our substitutions here. Let's see if we can put everything, replace all the y double prime and y in terms of x, and that should allow us to hopefully get k by itself, or solve for k. So y double prime gets replaced with this negative 25k sine 5x minus 32 cosine 4x. So all this is going to replace my y double prime. With my y, I'm going to replace y with this original equation, so 16 times k sine 5x plus 2 cosine 4x. The negative 27 sine 5x just stays that way. I'm going to distribute the 16 through, combine some like terms here, and once I do that, I see my signs can combine together. So negative 25k and 16k become negative 9k. The 32 goes away, negative 32 and 32 goes away. I'm just left with this negative 27 sine of 5x. So we have some matching parts. We should be able to solve for k. So I'm going to divide both sides by negative 9 sine of 5x. So when I do that, I get k by itself. The sine 5x goes away nicely. Negative 27 divided by negative 9 is just positive 3. Answer choice C. All right, number 5. Which of the following which are the solutions to the differential equation y double prime minus 10y prime plus 9y is equal to 0? So, yeah, this is a little bit tedious here because we need to find y prime and y double prime for each of these equations and see of these scenarios which one of these will allow for this statement to be true. So we have to go through the trouble of finding y prime and y double prime for each of these terms. So y prime for this term is just sine of u becomes cosine of u times u prime, cleans up to be 6 cosine 3x. Second derivative, cosine of u becomes negative sine u times u prime, which is negative 18 sine 3x. So now we have y prime and y double prime. We're going to plug both into the differential equation and see if that will give us a true statement. Y double prime gets replaced with the negative 18 sine 3x. Y prime here gets replaced with 6 cosine 3x. And here, if we try to combine these terms together, we get negative 18 minus 16 plus 18, and these do not combine to be 0. So we know this is out. Option 1 is out. All right, option 2, let's go ahead and find y prime and y double prime. E to the x becomes e to the x times 1, which is 5e to the x. Second derivative is also 5e to the x. So let's put these into this differential equation. Y double prime gets replaced with 5e to the x. This y prime gets replaced with 5e to the x. And then also this y gets replaced with the original equation, which is 5e to the x. Okay, so when we do that, we get 5e to the x minus 50e to the x plus 45e to the x. 5 minus 10 is negative 45, negative 45 plus 45, or we can just do 50 minus 50. Either way, we're able to get this to be a true statement. So we know option 2 does fulfill this differential equation. Okay, let's look at the third option. Ce to the 9x, c is a constant, so treat c like you would a number. The derivative for c to the x, ce to the 9x is ce to the 9x times 9, or 9ce to the 9x. The derivative here is just e to the 9x times 9 with a 9c in front, which becomes 81 ce to the 9x. So let's put all of these into our differential equation. Replace y double prime with 81 ce to the 9x. Replace the y prime with 9ce to the 9x. Replace the y with ce to the 9x. And when we do that, we get 81 minus 90 plus 9, and that does come out to be 0. So answer choice 2 and 3 will produce solutions that satisfy the differential equation, but not option 1. So answer choice D.